Hi, I'm Mike Bush. One of the reasons our results are so good.
If the beam drifts along the vehicle in the direction of travel while it's firing, the gun is fooled into thinking the vehicle is travelling faster than it actually is. Just watch this. Stationary car, what do you do?
Well, I have a stationary car, I've got a speed meter, let's see how fast the car's going. 8 miles an hour.
That's what enables us to do what we're here to do. And we all know what that is.
We do make mistakes. We're not perfect.
Ladies and gentlemen, boys and girls, shits and giggles. Well, as promised, for a bit of a Christmas present to you all, I was given a speed detection operators module. Let's see what it says. First published in November 2001. This study module is designed for New Zealand Police. It is for police training purposes only. And yet they don't follow their own training. Number one. So I've got a table of contents here, so they might be broken up into a few parts. I might do one part is for the radar, another part will be for the laser, traffic laser. The table of contents reads as such. 1 is about the module, 2 is the background, 3 is the radar speed detection, 4 is the self-pace test radar, 5 is the laser speed detection, 6 traffic laser, 7 self-pace test laser, 8 operating guidelines, 9 evidential requirements, 10 speed detection code of operations, 11 best practices guidelines radar, 12 best practice guidelines for laser, 13 practical application for radar, 14 practical application for laser, and 15 answers for self-pace test radar, and 16 answers for self-pace test laser. So the last two sections are where they can question themselves. Now, any operator must get at least 70% correct when tested on this, otherwise they fail. Let's have a look. Number 1, about this module. Goal. This module was designed to provide the theoretical basis for the safe and efficient operation of speed enforcement equipment. Objectives. When you have completed this module, you will be able to identify the requirements of the Code of Operations, explain pre-deployment testing, site selection, safety requirements, tracking history, and outline the evidential requirements for speeding offences. Module content. This module contains the following sections: background, radar speed detection, laser speed detection, operating guidelines, evidential requirements, speed detection code of operations, best practice guidelines for specific units, or for specified units, practical training, and self-paced test answers. Module and operator's manual. The manufacturer's operational manuals for radar and laser speed detection systems used by the New Zealand Police are inappropriate for the New Zealand environment. For this reason, this module and New Zealand Operator's Manual are the only documents detailing the manner of operation New Zealand operation. Should you have any questions or comments regarding this module, please contact Inspector Ron Phillips, Calibration Unit, Office of the Commissioner, and I've even got a phone number here. I won't put that out just in case. 2. Background. Introduction. Research has shown that speed is a major contributor to fatal and injury-causing road crashes. Research has shown, I would have thought that was fucking self-evident. If you drive faster, you're more likely to have a crash. But they use research. The government has identified increasing road safety as an important and core part of police policy. Significant improvements have been made in enhancing road safety in the last few years. The aim of New Zealand Police is to ensure this trend continues by using a range of tools including speed detection equipment, which don't actually lower people's speed. All it does is it generates revenue. Trained operators. For police members to use speed detection equipment, they must first be certified as a trained operator. To become a certified operator, you must A. Complete this module. Achieve a minimum of 70% in the module theory test. Undergo 20 hours practical instruction with a qualified instructor who will assess your competence, and be certified as a trained operator by the Traffic Operations Support Group or the Office of Commissioner. 20 hours have been allocated for practical training. The suggested breakdown of hours is 16 hours for radar training and 4 hours for laser training. So out of half a week, only 4 hours, half a day is for laser, and 16 hours or 2 days is for radar training. So it only takes 2.5 days to know how to operate these things. Supposed to be competent after that point. The Speed Detection Operators module focuses on the use of speed detection equipment. It provides an overview of the operating principles and policy guidelines governing the use of speed detection equipment. Evidential and administrative requirements are covered to ensure all operators are able to follow correct procedure. Follow correct procedure. Gotta wonder about that one, because they don't. Especially the cops that are pulling people over right next to change of speed sign areas. Within the module, there are 2 short tests. These are designed so that you can measure your progress. At the end of the module, you must sit a formal theory test that will be administered by district training staff. To pass this test, you must gain a mark of at least 70%. If you do not achieve this, you will need to revise the module and sit another test. So you don't just fail tough shit, that's it. No, they'll just put you through again. District training staff will keep a record of your test results and enter them into your training records. Training record, I'd love to see the training records. Practical. Once you have passed the test, you will need to gain practical experience operating the speed enforcement equipment. This will take at least 20 hours and needs to be completed with a qualified instructor. Your district trainer has a record of approved instructors. Wow. Whoopie-doo. The practical part of this training is very important and provides an opportunity for you to apply the theory in a practical setting. The qualified instructors have a training checklist they will use with you to guide your training and to assess your competence. A copy of this checklist is at the end of the module. When you have completed the practical training and demonstrated your competence in each area, the instructor will forward evidence of this to your district trainer. This will be entered into your training records. Certified as trained operator is the subtitle. Once you have successfully completed all parts of the training, you will be certified. In other words, you'll get a pretty bit of paper saying that you're clever. The district trainer will provide evidence of your training to the district strategic traffic manager. Gosh, they love their titles. Who will advise the traffic operations support group, officer of commissioner, who will issue a numbered certificate and enter your details onto the national database of trained operators. Now, I'd like to point out that it might make sense to make sure the QID number on that certificate of competency actually matches the QID number that's on the deployment register for the day. In some cases, possibly like mine, they don't. Right. You must be certified by the Traffic Operations Support Group and receive a certificate confirming you are the certified operator before you can use speed detection equipment. Really? I thought that was a no-brainer. If for any reason you require an additional copy of this certificate, you should contact the Traffic Operations Support Group immediately, or directly. Manufacturer's Manual. The manufacturer's operational manuals for various speed detection systems used by New Zealand Police are inappropriate for the New Zealand environment. They do not require a code of operations, ongoing device calibration, daily device testing, operator training, or a tracking history. Well, so that's what they don't require, the manufacturer's manuals. In other words, the manufacturer's manuals tell you what the device is, how it works and all the rest of it, but it doesn't tell you how you should use it in the particular environment it's being used. Sort of, again, not really a no-brainer, that one. Code of operations. In the interests of fairness, professionalism and accuracy, the Measurement Standards Laboratory of New Zealand Limited and the New Zealand Police have agreed to a code of operation that governs the operation of all speed detection equipment used by New Zealand Police. The Code of Operations 2001 is the current code and a copy is contained in this module. Using this module focuses on two types of speed detection equipment, radar and laser. Radar and laser describe the scientific methodology used to detect vehicle speed, although there are some similarities between the devices. There are also some fundamental differences. For this reason, this module looks at each type separately. The first part of this module deals with radar and the second with laser. It is important that you note the similarities and differences between the two types of device. Key information. The module contains a reasonable amount of detail. This is to provide depth to your understanding of how the device operates, or how the devices operate. You do not need to remember all the information contained in this module, no, just 70%. However, there are some important things that you must know. To help you identify the critical information, the relevant sections are marked Key Information in the left-hand column. Self-paced tests. Through the module you will find two self-paced tests. These are available for you to test your own learning. The answers to these tests are found at the end of the module. When you have finished the module and feel you have understood and can remember all the key information material you need to sit the assessment test. The assessment test. The assessment test is available from your district trainer. The test is administered in exam conditions. This means you will not have the module to help you and you will not be able to discuss the questions with others. You need to achieve a mark of at least 70% to pass the test. If this does not happen, you will require to resit the test, which will differ from the previous test. Or how much can it differ? Radar speed detection, part 3. Introduction. Radar is an acronym for radio detection and ranging. Radar means the transmission of radio waves that have the ability to detect and provide the distance the object is away from the transmission source. History. The concept of radar was first discovered in 1904, but it was during the Second World War that significant progress was made in this area of research. New Zealand scientists who had worked in this field during the war, returned to work for the Department of Science and Research and extended this technology. So it's all the old Second World War techs that sorted this out. The world's first working traffic speed detection radar was developed in New Zealand in the late 1940s. In 1947, the first traffic speed radar was trailed in London. From these humble beginnings, from these humble beginnings, radar devices have become an integral part of New Zealand road safety scene. Although the models have changed and will continue to change, the operating principles of radar devices remain the same. The use of radar as a speed enforcement tool is not restricted to New Zealand. Radar speed detection devices are widely used. Each over 15 million enforcement notices are issued to speeding drivers around the world. 15 million enforcement notices. Disgusting. Radar is present in everyday life. When we make a telephone call, use the internet, or watch television, the information is carried at least part of the way by microwave. Microwave is the radio frequency at which radars operate. Radar theory. The principle of primitive radar can be explained simply. A beam of microwave electromagnetic energy is generated at a super high frequency. This energy is radiated into free space through an antenna at the speed of light. At the speed of light. Do you realise the speed of light has changed over the years and that it's not actually constant? If you don't believe me, try shining light through water. See if it slows it down some. If you don't believe that one, go and look up an experiment called the Aries failure, where they used telescopes filled with water to slow down the starlight so they could measure to see if the Earth was moving. I'll give you the hot tip. It isn't. Aries failure was just that. It proved the Earth is motionless. But let's continue. This energy is radiated into free space through the antenna at the speed of light. If the energy strikes an object, part of the scattered energy is returned to the radar through the antenna. The unit processes the return signal and displays the information, the distance the object was from the antenna. Traffic radar. Traffic radar uses very low-powered, continuous microwave energy. The receiver monitors the transmitter frequency and compares the returned frequency with the transmitted frequency. The change of frequency is displayed as the speed check. The frequency change is due to the Doppler shift, which is explained later in the module. The receiver's electronics change the frequency into speed readings. Radar components. There are three basic components to traffic radar. 1. Transmitter. 2. Receiver. 3. Antenna. Key information. The three components that make traffic radars are transmitter, receiver and antenna. So that's the key information the trainee is supposed to get. To understand how traffic radar operates, it helps to know the function of each component. The transmitter. The transmitter generates radio energy into the microwave spectrum from a low-powered gun diode unit. This is the device used to make microwave energy. This energy is then channeled to the antenna with a small portion sent to the receiver for a comparison between the original transmitted signal and the received reflected signal. Key information again. The transmitter generates energy. Most of the energy is channeled to the antenna. A small amount goes to the receiver. The antenna. A narrow beam horn antenna is used to direct the microwave energy and collect the reflected signal. The antenna is aimed at the area to be monitored. The size of the antenna depends on the frequency or signal wavelengths used. Key information. The antenna is used to aim at the microwave beam at the area being monitored. And the receiver. The receiver is the device tuned to transmit frequency that picks up the waves generated by the transmitter. It amplifies the small signal detected and produces the information as a speed readout. Key information. The receiver is the unit that displays the speed readout. God, it's like these guys are like from primary school and they need it repeated to them. The radar beam. The beam of energy transmitted from the radar antenna is like a torch beam. The radar signal continues outward from the antenna until it is reflected or shined back. Refracted, bent like a pencil refracted or bent like a pencil placed in a glass of water and absorbed. Okay, so when you put a pencil into a glass of water, you notice the pencil bends. Okay, why? Because water bends light. It's not hard. It's a different medium than air. And yes, air is liquid. It's not just air. It's not thin air. It's water there. Anyway, we have a pretty diagram here of reflection. Boing boing. Reflection. Boing boing. Okay, and refraction, where it goes through and then sprawls outwards like a window screen. And then of course absorption, where it's just seeped straight into a living object like a tree and it's absorbed because you're just like microwaving something in your microwave oven. That microwave is absorbed by the food that's inside it. It doesn't get bounced around all over the place from it. Key information. The radar beam continues outward until it is reflected, refracted, or absorbed. Radar beam angle. The width of the radar beam is normally 12 degrees. So from 12 to 12:30, that is roughly 12 degrees, a little bit less. So it's just a smidgen of a beam. This is known as the main signal beam. The further the beam extends from the transmitter, the wider it becomes. Obviously. Right at the start, it's there. But when you come out a few 100 metres, it's gotten a lot wider. Okay? It's not a direct beam that shoots directly back. It's sent out as a sprawl, and whatever comes back, comes back. Okay? Key information. The main signal beam becomes wider the further the transmitter it becomes. Further from the transmitter it becomes. Beam range. The radar beam could continue outward from the antenna for an indefinite distance. However, in reality, really? So the previous bit wasn't reality? In reality, the beam range is the distance that the radar signal can be reflected back from the target to the receiver. The range differs depending on the site. Under ideal conditions, the device should be able to detect targets at a distance of 1 kilometre. So if you're starting off at 12 degrees, 1,000 metres down the road, I wonder how wide it is then. Come on. Key information. The range of the radar beam differs depending on the site. That's what it's supposed to take away from that. Not that the fact that it's only 12 degrees and it will detect up to 1 kilometre away. What bullshit. Factors affecting range. Atmospheric conditions such as rain, mist and fog will affect the radar range and the return signal. Local terrain such as hills, corners, fences and buildings will also have some effect. All radar units have a range or a sensitivity control that can be adjusted to control the level of the received return signal. By adjusting the range, you can reduce the target vehicle's distance. In other words, it doesn't have to be up to a kilometre, they can reduce it just to 50 metres away. Key information. The radar range can be affected by atmospherics and terrain. Operators can alter the range by adjusting the target range control. Target reflectivity. The size and shape of the target's vehicle surface will affect the information sent back to the radar unit for processing into speed readings. The bigger the target, the better it will reflect the signal back to the radar unit. A target vehicle that is small and aerodynamically designed is a poor reflector of a radar signal. This means it would need to be closer to the unit to be picked up clearly. Key information. The size and shape of the target vehicle affects the strength of the reflected signal. Not really a no-brainer, that one. The Doppler effect. The speed radar detects a movement between the transmitter and the received signal. This change in frequency is known as the Doppler effect. Simply, the radar unit determines the frequency difference between the signal transmitted from the radar unit and the signal reflected back from the moving target vehicle. Key information. The change of frequency between the signal transmitted and the signal reflected back is the Doppler effect. Tuning forks. Vibrating objects produce sound waves. A tuning fork illustrates how a vibrating object can produce sound, or a frequency as you might call it. The fork consists of a handle and two tines. When the tuning fork is hit, the tines begin to vibrate, causing disturbance in the surrounding air molecules and producing a ringing sound. This is why tuning forks are used as part of the calibration and daily testing of the radar unit. A particular speed reading is confirmed when the sound or frequency the fork produces is the same as the Doppler frequency required. Each fork is stamped with an operating band or frequency and the speed the fork will produce at that frequency. So they have a tuning fork for 30k, they have a tuning fork for 50, 60, 80, 100, and it's just a different sound being generated on your piano. You just hit a string, it creates that sound. Okay. And it's the change in sound. So you might send out you might get back which is slightly lower, and it will recognise the difference in frequency as a speed. Absolute bullshit. It is important to note that because the movement of air molecules from the fork goes from left to right, you should always present the side of the tines to the antenna. Isn't that interesting? Tuning forks should not be hit against hard objects, as the tines will bend out of shape and lose their ability to vibrate. The new flat type fork can be flicked a finger or lightly struck against another fork to produce the required level to conduct the daily testing. So in other words, you don't just bash it on the table and expect it to work, because you can knock these things out. Apparently just a small flick of a finger. So you might want to be careful when you're tuning them in. Key information. Tuning forks are used to simulate speed. Each fork is stamped with an operating band frequency and the speed the fork will produce at that frequency. They are used to check the accuracy of the speed readings. Cosine angle effect. In both stationary and moving modes, a cosine angle effect occurs when vehicles pass at an angle through the beam rather than directly in line with it. The cosine angle is the angle between the operator and the beam. The effect is that measured speed will always be less than true speed. This occurs because the measurement of speed will be equal to the true speed less that cosine of the angle between the beam and the direction of travel of the target vehicle. The larger the cosine angle, the lower the speed. At 90 degrees, there will be no reading, as there is no relative motion between the axis and the antenna and the target. So if they're shooting at you sideways and you're going that way, they can't measure it. It has to be less than 90 degrees. So you have to have a segment or a pi segment for that to happen. The cosine of the target travelling in a lane opposite the radar unit will always present a lower reading than is true, as the target will be off to the side of the main beam pointing down the road. Now, just so you can grasp this, this is saying that it's the speed they detect you at is apparently always lower than the actual speed of the target vehicle. Well, if that's the case, how are they proving beyond a reasonable doubt, which is the criminal standard, which is what you're there for? If you're there for a traffic ticket, it is considered a criminal offence. How can they prove beyond a reasonable doubt you were doing any speed? Because this is all guesswork. This is all depending on the cosine angle. You could be approaching them really closely and there'll be a higher cosine angle. The further away they are from you, the less cosine angle. Okay? Because if you're looking at a car that's 200 metres down a motorway, you're looking at it at a fairly straight angle. But as it comes closer to the lane next to you, the angle or cosine angle is more. Okay? It's just how that happens. And here's the pretty little picture that shows you what I'm talking about. The radar detector, the gun is shot here, and there's the approaching vehicle, and the distance there is the cosine angle. Okay? So if this car was closer, it would be shooting boom, boom, and that angle would be greater. Hopefully you get what I'm saying. The greater the cosine angle, the less accurate. The following table and diagram demonstrates the effect of the cosine angle. At 100 kilometers true speed of target, radar antenna offset to the angle of the target vehicle, speed and versus the speed in kilometers. At a zero angle, you're doing 100 k's. In other words, dead on, they're measuring you at 100 if it's tuned to 100. At a 10 degree cosine angle, it's 98.48 kilometers per hour. At a 20 degree cosine angle, it's 93 kilometers, or 93.96 kilometers. At a 30 degree cosine angle, they can only measure you, if you're doing it 100, they'll say you're only doing 86.6 kilometers an hour. And at a 40 degree cosine angle, you're only doing 76 kilometers an hour. I mean, that's quite a big difference, isn't it? So at a 50 degree or a 45 degree cosine angle, you must be only doing about 70. So if he's shooting at you and you're a 45 degree angle from him, he's not going to get an accurate reading. He's going to be three quarters correct probably. But again, that's hardly beyond a reasonable doubt that you're doing a specified speed that you're being alleged to be doing. As the table shows, for every degree the radar is offset to, the target vehicle and the speed reading registers less than the true speed of the target vehicle. The difference will always be in favour of the target vehicle. Right. Key information. Aiming the radar beam so that the cosine angle is minimised gives a more accurate reading. Any speed difference between true speed and the recorded speed will always be in the favour of the target vehicle. So they're saying that to make you think, oh, well, you were actually doing 140, but I only got you 120. Yeah, bullshit. These are questions you should ask. What was the cosine angle? You know, if it was a great cosine angle or quite a large cosine angle, say if he's using it on the motorway, they're trying to say that these devices can measure up to 6 lanes of traffic. Now, if they're parked, say, 4 or 5 metres off of the nearest lane, or the exiting lane, and you're on the 3rd or 4th lane over, if he detects you at 30 metres that way, each lane is 4 or 5 metres, so you're a good 35 metres away to the left, as well as 35 metres out, then you've got a 45-degree cosine angle there that he's trying to detect you on. How on earth is that accurate? It isn't. Okay? Where were we? Radar, stationary mode. Site selection is extremely important when operating radar in stationary mode. In other words, when you're sitting on your ass on the side of the road doing fuck all but sleeping. An operator must consider both operation and safety considerations when selecting a location. An ideal site is straight for about 200 metres or more, with the road surface slightly rising away from the radar unit and free from undulations. Undulations will cause fading of the return signal. Okay? Undulations, if it's wobbling like that, if the road's uneven, it's undulating. And they're saying within 200 metres. Well, I think I've already shown in previous clips how these scumbags sucking maggots like to sit just at the rise of a hill, like the Triangle Road one I showed on the 8th of November. He's parked less than about 70 metres away, where the hill of the road doesn't slightly rise. The road fucking dips away. Okay? Now that doesn't seem like that's following these guidelines, does it? So therefore, every ticket issued on the 8th of November by our friend EUR 591 on Triangle Road in Massey is void, because they hadn't set up their shit correctly, because he wasn't following his procedures or the manual. They do that to entrap people. So when you come up over a rise, you've got no chance in hell of slowing down when you see him. And if you're coming up over a rise, you're usually accelerating, especially on Triangle Road. At the start of Triangle Road, if you're at 60 k's or 50 k's at the top of Triangle Road, you don't have your foot on the accelerator. You actually have to change down a gear to keep it at 50, because the road is so steep, you will naturally speed up. And they like to sit halfway down. Rude. They have their little areas. They say they're high crash areas and it's an enforcement area. And it's bullshit. Okay. Key information: when selecting a site, operation and safety must be considered. Clearly. And let's bear in mind, the units in those stationary speed cameras are Rex radar systems, okay? So this is to do with them. The radar beam is like a torchlight beam. When setting up, the operator should aim the antenna slightly towards the right-hand side of the road. They should listen to the Doppler tone to ensure any targets are free from the fading that results if the antenna is poorly aimed or a poor site has been selected. The aiming of the beam is important to minimize the cosine effect and to obtain a greater return signal. Key information: correct aiming of the antenna minimizes the cosine effect. Range control. Adjust the range to control to require levels to monitor target vehicles. It's not very explanatory. Key information: the range control should be adjusted to suit the operational conditions. Interesting. Site safety. When setting up a stationary site, the operator should do so without interfering with other traffic movements. The site should allow the operator room to stop the offender using hand signals without the need for pursuit. Safe and legal parking should be available for the vehicle stopped. The operator must make sure they and the target vehicle and driver are safe when stopping them. Reflective jackets maximise the operator's visibility to the road users and enhance safety. They should be worn at all times. Key information: the operator is responsible for their safety and the safety of others on the road. On to radar moving mode. The basics of stationary radar apply to radar used in moving mode. However, there are some additional factors that must be considered. As a stationary radar, the antenna receives only one signal. However, in moving mode, there are two received signals, both with different Doppler return frequencies. Okay, so if they're actually following you, as opposed to sitting on the side of the road. Opposite lane mode. The operating principles of opposite lane mode are simple. A single radar frequency is transmitted from the moving patrol vehicle. A portion of this signal is reflected off the ground about 15 meters directly in front of the patrol vehicle and returned to the antenna. This is called ground speed and is displayed in the patrol speed window as low Doppler frequency shift. Because it's only 15 meters away, it's a very low cosine angle. The approaching target vehicle reflects a portion of the transmitted signal, which is high Doppler shift. Okay? So the 15 meters down that he's pointing at is your ground speed, which you must always zero out, and then they'll take the ground speed off of the speed of the approaching vehicle. Okay? As both the approaching target vehicle reflects a portion of the transmitted signal, which is a high Doppler shift. As both vehicles are moving towards each other, the Doppler shift frequencies combine. Example: a patrol vehicle travelling at 90 kilometers an hour and a target vehicle travelling at 130 kilometers an hour produce a combined speed of 220 kilometers an hour. However, with the radar's electronic processor units, the radar unit subtracts the patrol's ground speed from the combined speed, and this results in the target speed of 130 kilometers an hour. It is very important that the ground speed is obtained before any target vehicle enters the beam. Without a ground speed reading, the unit cannot produce a target vehicle reading. Operators must constantly monitor the patrol's calibrated speedometer to ensure the radar unit is displaying the correct ground speed. Ground speed may be lost due to heavy rain, as the rain droplets may absorb the radar signal. In this case, operation of the device should cease until rain eases or stops. And I've caught these fuckers working in the rain, eh? Ground speed. For the radar to operate in moving mode, it must be able to detect the ground speed of the patrol vehicle. There are times when the traffic radar is unable to process ground speed, and when this happens, the unit will show no speed readings. Ground speed will be lost if the vehicle being detected is travelling at the same speed as the patrol vehicle, there is heavy rain, the patrol vehicle is following a large vehicle, in which the case the ground speed beam may not obtain a reflection off the road, the range control is turned down too low. Key information: ground speed must be obtained before a target vehicle enters its beam. Same lane mode. Same lane mode is used for vehicles travelling ahead and in the same direction as the patrol vehicle. The unit calculates the difference between the ground speed of the patrol vehicle and the target vehicle, and this is depicted on the speed readout. Deployment. Tracking history. Something we should all remember. Obtaining a proper tracking history of the target will effectively eliminate errors. Tracking history for all radar contains three main elements. 1. Visual observation. The guy's got to be viewing your car speeding. 2. Audio confirmation. The Doppler tone. They should make sure they're locked onto the target. And radar verification, where the radar actually confirms what he's estimating the speed to be and what the Doppler tone's telling him. Visual observation. There are three parts to visual observation. The operator must 1. Identify the target vehicle and continue to monitor its travel. 2. Confirm the target vehicle is within the radar's range. 3. Estimate the target's vehicle speed. So when you're on a motorway and you're dishing out tickets, one ticket every 20 seconds, in that span of 20 seconds you've visually observed it, guessed it, got the Doppler tone, estimated the vehicle's speed. That's the tracking history so far for visual confirmation. Audio confirmation. There are three parts to audio confirmation. The operator must listen for a clear Doppler tone. In other words, there shouldn't be any wobbling or variation in the tone. It should be solid. 2. Check the tone is consistent with speed. Okay? And 3. Check the level of the signal heard is strong and not fluctuating in audio content. Like I say, it shouldn't be a wobbly sound. It should be a not a okay? Real easy. Sorry for the sound effects. Radar verification. There are three parts to radar verification. The initial reading is consistent with the operator's visual observation and the operator's estimated speed. 2. A steady target reading. 3. It says here, I'll just repeat this. Radar verification. There are three parts to radar verification. 1. The initial reading is consistent with the operator's visual observations and operator's estimated speed. 2. A steady target reading. 3. Reading consistent with visual observations and audio tone. In other words, your video and you visually estimate the audio tone solid. So now the radar verifies it. Oh, hang on. They said 3, but 4. Ground speed readings confirmed by the patrol speedometer. So if he's following you, this is in moving mode on the same lane, or the ground speed is number 4 of the radar verification. But that's just not, that's what they say. There are 3 parts, but there's actually 4.
You got the bonus blend.
Not that the police would get anything wrong. When the operator is satisfied the target vehicle is producing the correct reading, they should lock the target reading and take the appropriate enforcement action. It is not always possible to lock the target vehicle speed. However, failure to lock the speed will not prevent normal enforcement actions to be taken. Really? I mean, really? So you don't even have to lock the speed in? I would seriously question that bullshit. Possible sources of interference. In the super high frequencies of spectrum, where traffic radars operate at 24 to 38 gigahertz, the environment is relatively free of noise and other non-natural sources of interference. Okay, 24 to 38 gigahertz. Tell you what, we used to have things, well, going from an ex-Sky television satellite installer, where I've installed thousands of satellite dishes, the LNBF, or the low noise block frequency, the little doodad on the end of the rod that's pointing at your satellite dish where the cable plugs in, the low noise block, they are usually, they can vary between 11,300 gigahertz, 1,700 gigahertz, 10,750 gigahertz, 2,200 gigahertz. That's pretty fucking getting close there, isn't it? So it's pretty simple to think that perhaps satellite frequencies, which also travel in those gigahertz frequencies, and how they do it here is the exact same way that I would lock on to any satellite. I'd have the downlink frequency, I'd set my field strength meter to a frequency to detect it, and what I would do to find out the frequency, I would set my field strength meter to look into the satellite. I would know the download frequency, and I would know the LNBF frequency. I would take the low noise block frequency off of the downlink frequency, and that would leave me a difference of 1100 or whatever it was. And that was the frequency that I would set my field strength meter to. Combine the field strength meter with the low noise block, and it would equal the frequency coming from the satellite, or from the reflection of the dome, or whichever way you want to look at it. The environment is relatively free of noise and other non-natural sources of interference. Bullshit. However, interference may be experienced, as it is important to know how this occurs and what to do to eliminate it. Many articles have been written about the types of interference that will cause traffic radars to produce erroneous readings, including, ready for this? Street lighting systems, radar detectors, high voltage power lines, motor vehicle radiator fans. Really? Power transformers, neon signs, aircraft radar, and microwave ovens. So, if they clicked you anywhere near street lighting systems, radar detectors, high voltage power lines, which are fucking everywhere, motor vehicle radiator fans. Last time I checked, every motor vehicle has a radiator fan, and they're pointing they're pointing the radar straight at the front of your car, right where the fucking radiator fan is. These theories concern the New Zealand Police and the Measurement Standards Laboratory of New Zealand, the MSLNZ. Tests were conducted to determine if the potential interference sources listed above had any effect on the traffic radar equipments used by New Zealand Police. No effects were found. Really? So all of those articles are all wrong? Or the people that do the testing, that are probably got their dick halfway up the New Zealand Police's ass, have concurred with the police? That's nothing to worry about. We'll just ignore it. No effects were found. A point to consider is that airplanes contain more sensitive radar equipment than traffic radar units. If the items listed above generate significant interference, radar would be too dangerous for planes to use. So they're saying, if these things above that I said, street lights, radar detector, high voltage power lines, motor vehicle radiator fans, power transformers, if these things generated so much that it would affect their radar, then airplanes couldn't fly. That's their pathetic excuse for a reason why it's okay to use and stuff. They're not exactly 17 to 30,000 feet up in the air though, are they? Considering that the radar has a maximum range of about, what, 1 kilometre? I don't think so. Even though some conditions may cause the occasional intermittent readings, Most interference sources do not produce any Doppler tone. If a clear Doppler tone is obtained, this will help to eliminate possible sources of interference. By listening to the audible signal, the officer can determine when the target entered the beam, if the estimated speed of the target is consistent with the Doppler tone, and note the higher the tone, the faster the vehicle is. Radio transmitters. Radio energy detected near the traffic radar unit will blank off any target readings, displaying RFI. This tells the operator that radio energy is present. Really? But I thought it just said that radar doesn't interfere. The radio transmitters and that sort of shit doesn't interfere. But now it's saying it does. Because, okay, the radio energy from a patrol car's radio telephone or crosslink will prevent readings when the radio telephone is transmitted. Okay, so they can't be talking on their walkie-talkies and their radio telephones and use that because it interferes. Over the years, many people have tried to defeat radar speed equipment. There's really no need. They fuck up their shit so hard, you don't need to challenge that shit. You just need to wait for them to fuck up their paperwork correctly. Over many years, people have tried to defeat radar speed equipment. Most of these radio jamming devices do not work and are nothing more than gimmicks. Units that do work require large amounts of radio energy to be, I'll make sure I get my fucking magnetron out of my microwave and I'll stick that behind the grill in front of my fucking radiator and make sure that comes transmitting. Tell me if that interferes with these Doppler tones, dickheads. Transmitted and are prohibited in New Zealand by the radio communication regulations. Fuck off, quite frankly. I do whatever the fuck I like. If you want to prohibit it, prove it. Show me a contract where I've agreed to agree to that prohibition. Otherwise, I have the right to do whatever the fuck I like. Got me? Radar detectors. Radar detectors have a receiver that picks up the radar unit's transmitted energy and alerts the driver. Okay, so the little things that you have in your dashboards to detect if a radar is being used. Operating the radar in hold mode means the transmitter is turned off until required by the operator. The motorist with a radar detector cannot be alerted to the radar when it is operating in hold mode, so they don't send out a signal until they want to lock on to somebody. The operator can take the unit out of hold mode to obtain the speed check and produce a valid speed reading before the driver has time to react. Well, you know, that doesn't sound like entrapment at all. Of course not.
$8 miles an hour.
Clint Eastwood. I fucked them. Oh!